All right. Hi, everyone. Thank you for coming here. My name is Cameron, and this is Natalie. We'll be showing you something that we've been working on for the past few months, parallelizing Spectronaut and running it on the cloud across multiple virtual machines, which really speeds up the data pipeline for Spectronaut and also at lower cost. So here is an overview of what I will be covering today. So first, I will kind of just transit into the limitation of the regular directDIA when we were running it in a sequential manner. And then I'll explain how parallelization works. And then I'll do a head-to-head comparison in runtime and cost between the serial directDIA and parallelized directDIA. And I'll do a benchmarking on the identification and quantification because we wanted to make sure that after parallelization, we're getting a consistent result comparing to the serial directDIA. And then Natalie will cover on how to get started with your own cloud environment to start running these parallelized workflow that's available on GitHub. So here is a high-level summary of the library-free DIA proteomics pipeline. So like 3 major steps. So first, the sample preparation, because we're skipping the DDA library generation step. The sample preparation only takes like 1 to 2 days at this point. And then for data acquisition, thanks to the very high-performing instrument like the Astro or timsTOF, the data acquisition, depending on your acquisition rate, it could take 2 to 4 days on average. And then, but however, as we see the size of the proteomics studies continues to grow, we're more to realize that the directDIA analysis step is actually one of the most critical bottleneck in this entire data pipeline, and it's really slowing down the data turnaround time, and then it's just taking longer for us to get an actionable result for the next step decisions. And then the reason why with the conventional directDIA analysis it's taking so long is because clicker is not working. Second. Or I can just like click it. It's okay. Okay. Great. So as I said, for the conventional directDIA analysis, it usually takes 4 to 5 days and it costs like $400 to search 96 samples from one plate. And then the reason why it's taking so long and costs so more is because the conventional directDIA process samples on a sequential order on a single compute node. So as you can imagine, it doesn't process the next sample until the last one is completed. And then, so for a large scale proteomic studies where we have like hundreds of samples, the cost and runtime just grow exponentially as your study size grows. So to explain the directDIA workflow with some visuals, so when you run directDIA, actually 2 things happen. So first, Spectronaut generates a spectral search library using the Pulsar engine. And using this spectral library that's generated, it runs DIA analysis to generate the final result as SNE output. The parallelization strategy is conceptually really straightforward. So instead of doing this on a flat architecture, we're going to translate it into a vertical architecture to parallelize the Pulsar engine search and DIA analysis, which are the very compute-intensive steps. And then between them, we'll add like an intermediate step to combine the output into like one experimental level output. So here we're parallelizing these samples like by distributing them each to a single virtual machines on the cloud, and then we're sending them to the Pulsar search engine to generate a sample level search archives. So we have like n number of search archives being generated on their own VM. And then these search archive will be pulled together into one VM and then to generate a experimental level spectral library. and then the spectral library will be used to generate the DIA generate sample level SNE, and then these SNEs will be combined into experimental level SNE output. And everything looks very good and peaceful here. Really simple architecture, but when we tested it out, the fundamental shortcoming with this approach is that if you recall, like in the conventional directDIA, you calculate the FDR using the information from all the sample across the entire data set. So, but here, when you're generating the search archives, the FDR are calculated locally using only a subset of the file. So if you happen to have like one sample that's like a poor quality compared to the others, like that search archive will be having like a different FDR model. So when you put them together, eventually the result will be like the identification will be inconsistent because you're using a different FDR model as you're doing in the conventional directDIA, where the FDR is calculated globally. So to counter that limitation, Spectronaut, the version 20.3 Spectronaut introduces a new parallelization architecture. So what's different is that in this new architecture, the pulsar step is being split into like a few extra steps. So starting with the initial search archives, it's still being generated using the pulsar engine in their own virtual machines in parallel. And then instead of just like directly creating the spectral library from these independent search archives, we're pulling these initial search archives together and then to calculate a FDR optimization model. So now you have a unified global FDR optimization model, and then we're feeding this model back to their own VM and then regenerate the search archives against one harmonized FDR model. So this ensures that kind of like mimicking how the conventional directDIA generates its FDR model across the entire data set. And then eventually we're doing the combine step to combine all these final FDR corrected search archives into a final spectral library. And then the DIA analysis step is the same as before, just sending that spectral library and then doing this DIA analysis. And this, as I said, ensures like a more consistent identification outcome compared to the original architecture that was used in the previous versions. So before I get into the benchmarks, I'll just show you how much how much this parallelization improves the runtime and cost, as I mentioned in the overview slide. So here is we're looking at a runtime as a function. Yeah, we're looking at runtime as a function of number of files searched. So this curve is the serial workflow where we're searching things in a sequential manner. And then when we're doing parallelization, we're actually, this is the curve for parallelization. So we're achieving a 6 times faster runtime when we're searching 500 files. And then this gap only grows because the serial workflow will grow exponentially. And then the parallel workflow, as you can see, the curve is relatively flatter than a serial. But at the other hand of this balance to speed is the cost, and then parallelization is no exception. So in our benchmark runs, we found that the parallelized workflow costs roughly twice as much as the legacy workflow. So as you can see on the left, the serial workflow costs $20 to search 10 samples. However, the parallelized workflow costs $40. And at this price point, if you want to do this for even larger scale experiments, this price point is not sustainable and practical for most research labs. And this is because the standard cloud infrastructure that we run, we used to run directDIA on are the standard instances. And then they become very expensive when you're distributing tasks to individual VMs. So instead of starting one virtual machines, now you're starting hundreds of virtual machines. But however, what's unique about the parallelized architecture is that instead of running that one big chunk of directDIA task, which takes like a few days to run, now we're running them in segments of mini tasks. So as in the yellow highlighted rectangles are the tasks that are being parallelized. And then these tasks only take 1 hour for each sample to run. And coming back to the standard instances, the reason why I bring it up is because there's another type of instances on the cloud called preemptible instances. And what's different between the preemptible instances and then the standard, like the major difference is the preemptible instances are up to 91% cheaper than the standard instances. But in exchange, they can be terminated at any time according to the cloud traffic. So it's kind of like a flash sale that when they have like empty machines, they just rent it at like a lower price. But don't panic. Like if they got terminated, they will be restarted automatically, so you don't have to worry about it. It's just like start from scratch and then like just rerun the entire task. But this type of machines, like these type of preemptible instances, was not suitable for directDIA because, as you can imagine, like when you run directDIA for days, you don't want it to be terminated in the middle of it, like after 3 days of running, after costing like $200, and then you are just like restarting from the scratch. But however, for these very short mini tasks, like only run for like an hour, they're actually affordable to exchange the uncertainty for a much cheaper price when running them. So here we, in this new parallel workflow, we're running these yellow highlighted tasks on preemptible instances, and then this is what it does to the cost. So instead of $40 when we're running on the standard instances, now we're driving down the compute cost to less than $10, which is actually even cheaper than the serial workflow, which originally cost like $20. So this means, combined with the runtime improvement, this means that the parallelized workflow is now faster and even more cost-effective comparing to the serial directDIA that we used to run. And this is very exciting because it's faster and it's cheaper. Like we're breaking that cost and runtime trade-off. So coming back to the curve plot, now we're plotting the cost as a function of the number of files searched. The parallelized workflow running on preemptible instances is 30% cheaper than the serial workflow at 500 files. And then the gap only becomes wider as the study size grows. And then there's like a kind of like a factor of luck here. So if, let's say if your preemptible didn't get terminated, the cost could become even lower. So there's like a wider variation there. But the bottom line is that now the runtime and cost improvement makes the large-scale directDIA searches more practicable to run in a cloud environment. And then with the parallelized workflow carrying out at this speed and cost, the next question naturally will be how consistent are the IDs and quants comparing to the serial workflow? So to benchmark the parallelized workflow, we collected a set of 10 independent jerk QC samples from both the Thermo's Astro and Bruker's timsTOF HT, just representing two of the most widely used instruments for DIA proteomics. And then we searched these data using both the serial and parallelized workflow, and then we just like compare them head to head. So starting with the IDs, across both instruments, the parallelized workflow is reporting a very highly consistent result at the precursor, peptides, and protein level tiers, and then it's closely matching the serial workflow at every tier. As you can see, there are very similar numbers that they're reporting. And for quantification, we're plotting the protein intensities from the parallelized workflow on the y-axis, and then from the serial workflow on the x-axis, and then we're calculating the correlation coefficient, and then we're seeing a very strongly correlated protein quants between these two workflows. So we're very confident that the parallelized workflow doesn't sacrifice the analytic performance for the speed and cheaper cost. So for the next part, Natalie will be demonstrating how easy it is to getting started to run these workflows in your own cloud environment.
Thank you, Cameron. Yeah, so as Cameron mentioned, we have this workflow available on GitHub. We'll share the GitHub repo with the QR code at the end. And currently, the workflow architecture is written in the WDL language, which allows you to immediately deploy the workflow that we've written to a number of cloud platforms, such as AWS through Manifold. We are also working on porting this workflow to Nextflow so you can use it with, for example, Microsoft Azure. But today I'm mostly going to talk about Terra, which is our on-site cloud-based platform that we use a lot at the Broad. And the reason I want to highlight Terra is that Terra has a nice web interface that is really easy to hop into if you're somebody who doesn't have a lot of cloud computing or computational experience. So to you, the user, what you're going to see is a graphical interface where you can point, you can click, you can upload files, you can run workflows without having to kind of get into all the muck of looking at a workflow, looking at a Docker, things like that. So that's why I think that the Terra platform is a nice way to get started with Spectronaut parallelization on your own. So for those of you who are unfamiliar with Terra, this is the link to Terra. They have a lot of tutorials on their website to help you get started. To start on Terra, it's really as easy as logging in with the Gmail account and linking some sort of billing account so that you can pay for your cloud services. Terra is synced with the Google Cloud Platform architecture. So if you're familiar with GCP, a lot of the resources you use on Terra will be familiar to you as well. The two main terminologies that are used in the Terra environment are workspace and workflow. So a workspace you can think of as like your project directory. So you can think of it as like a folder on your desktop. This is a space that's going to host all of your scripts, all of your files, and everything that you need to actually run your jobs and get your results back. A workflow is a script inside your workspace. So this is how you are actually going to execute the Spectronaut search, is through using a workflow within your workspace. And the nice thing about workspaces is that they are shareable between different users. So if you have a team of people who wants to work on Spectronaut searches together, you can create one unified workspace where you have all of your data and all of your runs together for reproducibility and also to help track your costs and your analysis. Creating your workspace on Terra, again, it's very easy. You click a button, you put in your information, and then boom, the workspace is created for you. You don't have to sort of muck around with things in the background. In terms of what you can see from your workspace dashboard, you can get information such as who owns the workspace, who the workspace is shared with, and most importantly, if you have information about your Google Cloud bucket that stores all of your files as well as storage costs. So you have a bird's eye view at how much you are spending on storage costs within your workspace bucket. So you have your workspace set up and you're ready to run Spectronaut. What do you do next? So on GitHub, we have the workflow ready to go. You will just need to add your license key. We provide instructions on our GitHub to instruct you on how to add your license key. It's a pretty straightforward progress. And then once you do that, you upload your workflow to your workspace and you are ready to start searching with Spectronaut. In terms of setting up your search, there are input fields for all of your parameters. Required parameters are bolded, so you sort of know what you need to have or what you can skip. The parameter upload is done using a JSON file. So if you're familiar with JSON files, you can also download, upload JSON files so you can reuse parameters very easily. And then there are certain cloud-based options that you can select when you're going to run your workflow. One of these is call caching. So how call caching works is, let's say that you start your workflow, you go through those 6 steps that Cameron showed you, something happens on the cloud, and after step 2, your job fails. I don't know, maybe the server went down or something. If you have call caching, what this means is if you were to restart your job, it's actually going to restart your job from the point of failure. So if you got through step 2 and it failed at step 3, it's going to restart at step 3. You don't have to re-spend all the time and resources to do the first 2 steps. So this is a really nice way to save costs and also time that's built into the Terra architecture. We also didn't really have time to talk about today, but another feature of the parallelized workflow is for those of you who use HTRMS conversion, that is actually also built into the workflow. you can convert your files to HTRMS within our workflow. It's just a toggle. There's a toggle that's like HTRMS conversion on or off. If you do that, it takes about 20 minutes to convert as many files as you need because that's also parallelized. So if you work with that format, that option is in here as well. All of your jobs are going to show up in a history tab. So this is great if you ever need to go back and figure out, when did I run this set of files? How much did it cost? There's a really nice way to get to that. If you click on one of these jobs, it's going to take you immediately to a job manager page where you can jump directly to whatever section of the bucket contains your output files. So this is another nice way graphically that you can sort of manage your usage and your runs. So to conclude, our parallelized workflow is up to 6 times faster and 30% cheaper than the serial workflow. We validated on both Astral and timsTOF HT systems. Here is the QR code to our GitHub page, which has everything you need, the Docker, the workflow, really detailed README to help you get started on Terra or whatever cloud platform of your choice. And I really would like to thank, we had a lot of help with this, especially a lot of people in the proteomics platform, which helped us with feedback, with testing. We really appreciate it. And also for our colleagues at Biognosis who helped us get this set up. And with that, we're happy to take a few questions. Thank you.
Hi, I have a question for Cameron. Great talk. I'm wondering if you could elaborate a little bit the 6 times faster for your cloud setup, the parallelization. How many seats do you guys set up for that?
Yeah, that's a good question. So, so usually when we're talking about parallelization, we're doing like 1 file per VM, but each VM takes like 1 token. So for users that have like limited token availabilities, we have this like flexible binning methods that you can set your the number of batches of file that you are parallelizing very flexibly, and then you can so basically like if you have like 500 files, and then you can set your seats to only like 5, and then it's going to like distribute those like 500 files into those like 5 VMs in parallel. So it's very flexible for you to set it up at whatever token budgets that you have.
So you are saying that regardless the seat you are setting up is going to be 6 times faster? Or you are saying that
so 6 times faster is the maximum. So
maximum, it's like unlimited seat.
Yeah, so if you have unlimited
seat
seat,
available. Okay.
yes.
Yeah.
Okay.
Yep.
So if you have limited seat, that will be different. Do you guys have a
Yes.
like an idea what if you have 100 seats, what the increase will be?
So just for the speed, I would say that the recommended files per VM is like around 2 to 5 files per VM, and then usually you'll definitely not get like 6 times faster, but it's still every file takes like about like an hour to process in those parallelized tasks. So if you are having 5 files in every VMs, then for every of those like mini tasks, you are spending like 5 hours. So I would imagine like your runtime would just like increase by that fold.
We did do some testing with
Right.
more files in each VM. We'd be happy to show you kind of what we came up with there. We also did some tests such as when you partition the files into the VMs, that's always the same. So if you were to run the job again, you're always going to have the same files partitioned in the same way. And we also made sure that no matter sort of how many VMs you use or how many files per PMs you use, your results are going to be consistent. And that has to do with the updated architecture that Cameron talked about. That enables us to make sure that no matter how many tokens or seats you're using, your results are going to be consistent with this architecture.
I see. Thank you so much.
Thank you. So you showed a really nice graph showing the 30% improvement in speed with the parallelization by the time you get to 500 runs. And I'm sort of wondering, not every, and I see there's a benefit at 100 runs. how many runs at a minimum do you think you need to be searching per project in order to see a benefit? Because not every project that I do is 100 files or more.
Definitely, great question. Well, I'm using it just at the recent times. So what I would notice, the improvement in runtime and cost will be just like starting from about like 25 to 30 files. Because like it used to be taking like a few days to search like 36 files, let's say. But now with the parallelized workflow, it only takes like probably just overnight, and then you have the result. So we started to see improvement at that level, and then you'll just see better results for like larger experiments. But definitely, but like if you're running the parallelized workflow on like only 10 files, the overhead will kind of like just kind of cancel the benefits of the parallelization. So you won't get like a very obvious improvement in the runtime and cost. So yeah, great question.
I have a practical question that we also encounter. So if you have more than 100 files or 100 raw files, how you are able to visualize this data? Because the normal VM or a single license Spectronaut will actually crash. So if you have 500, do you have a solution for visualizing this data?
That's a good question for diagnosis people. Yeah, we also have that. We also have that problem. So when we're trying to when we're combining the SNE file from like more than 200 SNE files from per VM, we are seeing that like it just exceeding the memory cap. Yeah, so that's a good question for diagnosis.
Just last question. All your work is Windows-based? Because we're using Nextflow, which is Linux, so we see in the performance is even is faster. Mm-hmm. Is it what you have all Windows-based, or you have a Linux solution?
So these are all running on Linux systems.
Linux systems.
Yes. Okay. So yeah.
Okay.
And then for the next step, probably the next push on GitHub, it will be we're planning to translate it into Nextflow, so it's more compatible with more cloud platforms instead of just limiting to Terra.
Thank you.
Great talk, thank you. I had a question about the head-to-head that you did with the standard workflow where you're comparing 10x files, I think. Do you know if that will hold if you go to 100, 200, 500 files?
So we hasn't done that yet, but we will imagine it will be the same, because testing like 100 files will be like very expensive. And
yeah,
so.
We don't know, but we would expect this similar consistency. Yeah.
Yeah.
Thank you.
Okay, if we don't have any more questions, thank you very much again, Cameron and Natalie.